Clean room model. In this video, we are going to see about clean room model. Definition. Clean room software development is a software development philosophy which is based on static verification techniques. The objective of this approach to software development is zero-defect software. The name clean room was derived by analogy with semiconductor fabrication units. Clean room defects are avoided by manufacturing in an ultra-clean atmosphere. It has three foundations: incremental development under statistical quality control, software development based on mathematical principles, software testing based on a statistical principle. The clean room approach to software development is based on the notion that defects in software should be avoided rather than detected and repaired. It relies on a strict, formalized inspection process to discover faults before the software is tested. There are 5 key characteristics of the clean room development process. Formal specification, incremental development, structured programming, static verification, statistical testing. Category: specifics. Evaluation of goals. Focus on accuracy, reliability, reducing ambiguity, incompleteness, inconsistency. Methodology. Mathematical transformation and statistical testing of usage profiles. Technology. Facilitated by software automation. Critical factors. Specification language. Interdisciplinary effects. Mathematical specification, statistical sampling, project management. Behavioral considerations. Peer review teams. Problem nature. Complex systems. Application domain. General. Clean room software engineering technology. In this video, we are going to see about clean room software engineering technology. Incremental development lifecycle. Clean room management is based on development and certification of a pipeline of user function software increments that accumulate into the final product. Incremental development enables early and continual quality assessment and feedback and facilitates process improvements as development progresses. The incremental approach avoids risks inherent in component integration late in the development cycle. Incremental development permits systematic management and incorporation of requirements changes over the development cycle. The technical basis for incremental development in clean room is the mathematical property of referential transparency. In the context of software development, this property requires that a specification and its design decomposition define the same mathematical function, that is, the same mapping from the domain of inputs to the range of correct outputs. When this property holds, a design can be shown to be correct with respect to its specification. In practice, the requirement for referential transparency places constraints on the functional content and order of design decomposition of a software system. User functions are organized for development into a sequence of verifiable and executable software increments, each providing additional function. The functional content of the increments is defined such that they accumulate into a complete set of functions required for the final system. Architectural requirements and risk avoidance strategies place additional constraints on increment content. For correctness, each increment must satisfy its parent specification through the functions it provides combined with the subspecifications it contains for future increments. Functional specification and design. In this video, we are going to see about functional specification and design. A functional specification (FS) is a formal document that details all features and specifications of a certain software product. To assess how the system will impact future business operations, the customer must understand what processes will be performed by the system and how the users will interact with the system. The functional specification includes the following: a description of each business process performed by the system, a data flow diagram showing the flows of information between these processes, definition of the flow of information between the users and the system, references to screen and report format, the project team begins developing the functional specification by analyzing the customer's requirements and developing a logical model of a proposed system. This model defines what functionality will be provided to the customer without considering implementation constraints. Once a logical model has been developed in an initial version of the functional specification, the project team outlines a physical model in the system design specification. This physical model is a sum of all the tangible elements of the automated system, including the user interface. Then, the team includes the screens and reports in the final version of the functional specification so that the system can be visualized by the customer. The functional specification documents what is to be done from a system perspective to meet the customer's requirements, and therefore it must address each of those requirements. Accurate traceability is important between the requirements and the functional specification, designs, and tests. The project team should use appropriate tools for this task, if they are available. Otherwise, the team should consider developing a traceability matrix which contains sections and paragraph numbers from the requirement specification relating them to the corresponding sections of the functional specification. The customer should validate and approve any such matrix developed. Scope of the functional specification should correctly define all of the functions performed by the software and all of the constraints on the execution of those functions. A software constraint may exist because of the nature of the task to be solved or because of a special characteristic of the project. Should not describe any design or implementation details that are not apparent to the user of the software. Internal design or implementation details should be described in the design stage of the project. There are a number of other plans and documents that reference the functional specification. Some of the key documents that are guided by functional specification are design documents developed by the development team, test plan or test cases for use by quality assurance team, end user documentation. Functional specification will typically need to evolve as the development of the software product progresses. It may be impossible to specify some details at the time the project is initiated. For example, it may be impossible to define all of the screen formats for an interactive program during the requirements phase. Purpose. The primary purpose of the functional specification is to provide a single formal specification of the scope of the software solution from the customer's business perspective. An important document, the functional specification provides the basis for designing, developing, and implementing the solution, including cost and schedule. Once the functional specification is completed, any new functionality required must follow the change control process before the scope of the software solution can be expanded. A secondary purpose of the functional specification is to specify factors that affect the design, development, testing, and implementation of the system. These specifications include environmental factors such as personnel affected, sites involved, documentation required, training required, and any other issues identified by the customer. Overview of the functional specification. In this video, we are going to see about overview of functional specification. The functional specification translates customer requirements into a precise specification of what the solution provider will actually build and deliver. Those team members developing the functional specification should remember that this is likely to be the first detailed description of the system seen by members of the solution provider's project team and the customer. Since the document will often be read by non-technical people, it should have a thorough overview and should introduce system detail and special terms gradually. Level of detail required. The following question should be used as a measure of the appropriate level of information in any functional specification. Are all external interfaces, that is, all screens and report formats and all interfaces to other computer systems described? Is there sufficient detail to permit the design to start without further interaction with the customer? Does the specification describe the business functions but not the system internal design? Does it describe what business functions the system performs? Can an acceptance test specification be created from the functional? In other words, are all specifications measurable? Because the functional specification is a binding document, care must be taken to be clear, concise, and direct. Words should be chosen so as to avoid unnecessary obligations. All statements must be provable. Example: avoid words such as instantaneously and optimally. Statements should be in the present tense and written in the third person omniscient. Structured analysis. The development of the functional specification occurs within the frameworks of the structured system analysis process. This process constructs 4 different models or views of the system. Refinement of the system design. As explained previously, establishing the system design specification is a process that both affects and is impacted by the functional specification effort. The functional specification provides a logical model of the system, which is used in developing the system design specification to build a physical model down to the level 1 DFT. Subsequent levels of detail are then added to the logical and physical models in the functional specification and system design specification respectively. Specification of acceptance test. A consensus is reached on the functional specifications of the system. The project team can establish and document criteria for the demonstration of system functionality that precedes final acceptance of the software solution. These tests of functionality are outlined in the acceptance test specification. Successful execution of the acceptance test confirms that the system conforms to the functional specification. Guidelines. The following guidelines will help in the production of a testable functional specification. When describing what to build, also consider how to prove that it has been built. Describe the features and goals of the system in verifiable terms. Identify any system external parameters. List the non-goals for the system. Revision of project planning. Once the functionality and design of the system have been finalized, the project manager CAB revises and tightens the project plan to cover the rest of the project's life cycle. Functional specification process. Organize functional specification effort. Collect customer information. Develop proposed logical model. Define environmental specifications. Define quality specifications. Define general specifications. Develop detailed proposed logical model. Develop publication specifications. Define customer training specifications. Define system limitations. Define customer implementation responsibilities. Finalize functional specification. Review and approve functional specification. Output. Resources committed and ready to begin work. Customer interview plans confirmed. Collect customer information. The objective of this activity is to collect all of the information needed by the solution provider to gain a better understanding of the customer's environment and requirements. During this step, the solution provider conducts interviews with key customer personnel. Full understanding of the customer's environment, current business processes, the data used to support those processes, and the requirements that affect those processes is key to the success of the proposed system. At the conclusion of this step, all the interviewing and data collection to finalize customer requirements should be finished. Thus, though interaction between the solution provider and the customer continue, the project team should be careful not to commit to providing additional functionality requested by the customer after this time. Component-based software engineering, CBSE. In this video, we are going to see about component-based software engineering, CBSE. Component-based software engineering, CBSE, is an approach to software development that relies on software reuse. It is emerged from the failure of object-oriented development to support effective reuse. Single object classes are too detailed and specific. Components are more abstract than object classes and can be considered to be standalone service providers. Independent components specified by their interfaces. Component standards to facilitate component integration. Middleware that provides support for component interoperability. A development process that is geared to reuse. A component-based development model was used to illustrate how a library of reusable candidate components can be integrated into a typical evolutionary process model. The CBSE process, however, must be characterized in a manner that not only identifies candidate components but also qualifies each component's interface, adapts components to remove architectural mismatches, assembles components into a selected architectural style, and updates components as requirements for the system change. Definition: a software component is a software element that conforms to a component model and can be independently deployed and composed without modification according to a composition standard. A software component is a unit of composition with contractually specified interfaces and explicit context dependencies only. A software component can be deployed independently and is subject to composition by third parties. Why reuse is important? Software reuse is based on higher quality components, therefore has become popular in academia and the software industry because of the advantages of reducing development costs and time. Companies such as IBM, Lucent Technologies, and GTE launched enterprise-oriented software reuse projects to develop in-house reusable components libraries. The major purpose was to speed up production lines of application system based on in-house reusable components so that they could keep pace with market forces and increases their competitive edge in a business market and copes with dynamic business needs and fast updated technologies. Since 1995, the information technology and service market has grown rapidly because of the explosive popularity of the internet and fast technology advance. This market change created a strong demand for new large-scale information service systems and e-commerce applications over the internet. To fulfill this demand, the software market and industry had to change in order to deliver large web-based information service systems and e-commerce applications on a very tight schedule based on commercial off-the-shelf COTS components. The tragic events of September 11, 2001 destroyed and damaged many business application systems and infrastructures. This has driven a strong demand for setting up new secured application systems and information services to replace out-of-date systems in businesses and government agencies. Most systems are global distributed information service systems with a complex structure and multiple platforms. They have strict system requirements for reliable and scalable functional services. It is very difficult or even impossible for software workshops to develop new IT-based application systems and serviced infrastructures without using COTS components. To reduce development cost and time, they must use a component-based software engineering approach to develop new systems or upgrade existing systems based on high-quality reusable components. Objectives of component-based software engineering: reduction of cost and time for building large and complicated systems. Main objective of component-based approach is to build complicated software systems using off-the-shelf components so that the time to build the software diminishes drastically. The cost effectiveness of the current method can be analyzed using function point or other methods. Improving the quality of the software. The quality of the software can be improved by improving the quality of the component. Though the concept is not true in general, sometimes quality of the assembled systems may not be directly related to quality of the component in sense that improving the quality of the component does not necessarily imply the improvement of the systems. Detection of defect within the systems. Component approach helps the system to find its defect readily by testing the components. But the source of defects is difficult to find in case of component development approach. Domain engineering. In this video, we are going to see about domain engineering. Domain engineering includes three major activities: analysis, construction, and dissemination. It can be argued that reuse will disappear not by elimination but by integration into the fabric of software engineering practice. As greater emphasis is placed on reuse, some believe that domain engineering will become as important as software engineering over the next decade. Domain Analysis Process (DAP). Structure modeling and structure points. Structural modeling is a pattern-based domain engineering approach that works under the assumption that every application domain has repeating patterns that have reuse potential. According to Polar and Risman, structural model consists of a small number of structural elements manifesting clear patterns of interaction. The architectural of system using structural model are characterized by multiple ensembles that are composed from these model elements. Many architectural units emerge from simple patterns of interaction among this small number of elements. Structural point is a distinct construct within a structure model. Structural points have three distinct characteristics. A structure point is an abstraction that should have a limited number of instances. Restating this in object-oriented jargon, the size of the class hierarchy should be small. In addition, the abstraction should recur throughout the applications in the domain. The rules that govern the use of the structure point should be easily understood. In addition, the interface to the structure point should be relatively simple. The structure point should implement information hiding by isolating all complexity contained within the structure point itself. This reduces the perceived complexity of the overall system. Characterization of structure points. It should have a limited number of instances. Interface of the structure point should be relatively simple. Structure point should implement information hiding by isolating all complexity contained within the structure point itself. Software reuse. In this video, we are going to see about software reuse. Software products are expensive. Therefore, the project managers are always worried about the high cost of software development and are desperately looking for ways to cut development cost. A possible way to reduce development cost is to reuse parts from previously developed software. In addition to reduced development cost and time, reuse also leads to higher quality of the developed product since the reusable components are ensured to have higher quality. A reuse approach that is of later gaining prominence is component-based development. Component-based software development is different from the traditional software development in the sense that software is developed by assembling software from off-the-shelf components. Software development with reuse is very similar to a modern hardware engineer building an electronic circuit by using standard types of ICs and other components. What can be reused? It is important to deliberate almost the kinds of the artifacts associated with software development that can be reused. Almost all artifacts associated with software development, including project plan and test plan, can be reused. However, the prominent items that can be effectively reused are requirement specification, design, code, test cases, knowledge. Knowledge is the most abstract development artifact that can be reused. Out of all the reuse artifacts, reuse of knowledge occurs automatically without any conscious effort in this direction. However, two major difficulties with unplanned reuse of knowledge is that a developer experienced in one type of product might be included in a team developing a different type of software. A planned reuse of knowledge can increase the effectiveness of reuse. For this, reusable knowledge should be systematically extracted and documented, but it is usually very difficult to extract and document reusable knowledge. Basic issues in any reuse program. The following are some of the basic issues that must be clearly understood for starting any reuse program. Component creation, component indexing and storing, component search, component understanding, component adaptation, repository maintenance. Reuse initiation and approach. In this video, we are going to see about reuse initiation and approach. Reuse initiation. Existing software has to be analyzed in order to find, evaluate, and select potentially reusable software components. The components may need to be generalized and are complemented with specific reuse documentation. Then, they need to be stored in a repository to serve as the base of reusable components in the organization. The effort needed to perform these tasks will vary depending on the scope of the reuse program to be installed. This may range from a part-time individual at almost no cost to the installment of a separate organization unit. Especially in the latter case, support from top management is essential because initial costs face a slow return on investment. Not every component that is reusable will be considered in this initiation step. Thus, categories of reusable components should be identified and prioritized. It is important to acquire components that are important for the business. Assigning components to different levels of generality can be useful in this context. Reuse experiment. Risks and costs are reduced by starting with a reuse experiment. This will facilitate learning about technical and organizational issues that impede the reuse program. The experiment can be done with an ongoing project as well as with a new one that is to be approached with a reuse. It is important that success criteria be defined and measurements be taken for the experiment. The project should not be too long so that results are not delayed too long. Depending on the results, the reuse program should be extended or reworked. Reuse approach. A promising approach that is being adopted by many organizations is to introduce a building block approach into the software development process. For this, reusable components need to be identified after every development project is completed. The reusability of the identified components has to be enhanced and these have to be cataloged into a component library. It must be clearly understood that an issue crucial to every reuse effort is the identification of reusable components. Domain analysis is a promising approach to identify reusable components. Domain analysis. The aim of domain analysis is to identify the reusable components for a problem domain. Reuse domain. A reuse domain is a technically related set of application areas. A body of information is considered to be problem domain for reuse if a deep and comprehensive relationship exists among the information items as characterized by patterns of similarity among the development components of the software product. A reuse domain is shared understanding of some communities characterized by concepts, techniques, and terminologies that show some coherence. Evolution of a reuse domain. The ultimate result of domain analysis is development of problem-oriented language. The problem-oriented languages are also known as application generators. These application generators once developed from application development standards. The domain slowly develops. As a domain, we may distinguish the various stages it undergoes. Stage 1. There is no clear and consistent set of notations. Obviously, no reusable components are available. All software is written from scratch. Stage 2. Here, only experiences from similar projects are used in the development effort. This means that there is only knowledge reuse. Stage 3. At this stage, the domain is ripe for reuse. The set of concepts are stabilized and notations standardized. Standard solutions to standard problems are available. There is both knowledge and component reuse. Stage 4. The domain has been fully explored. The software development for the domain can largely be automated. Programs are not written in the traditional sense anymore. programs are written using a domain-specific language, which is also known as an application generator. Reuse at organizational level. In this video, we are going to see about reuse at organizational level. Reusability should be a standard part in all software development activities, including specification, design, implementation, test, etc. Ideally, there should be a steady flow of reusable components. In practice, however, things are not so simple. Extracting reusable components from projects that were completed in the past presents. An important difficulty not encountered while extracting a reusable component from an ongoing project: typically, the original developers are no longer available for consultation. Development of new systems leads to an assortment of products, since reusability ranges from items whose reusability is immediate to those items whose reusability is highly improbable. Achieving organization-level reuse requires adoption of the following steps. Assess of an item's potential for reuse. Refine the item for greater reusability. Enter the product in the reuse repository. Refining products for greater reusability. For a product to be reusable, it must be relatively easy to adapt it to different contexts. Machine dependency must be abstracted out or localized using data encapsulation techniques. The following refinements may be carried out: name generalization, operation generalization, exception generalization, reengineering. In this video, we are going to see about reengineering. The process of system evolution involves understanding the program that has to be changed and then implementing these changes. However, many systems, especially older legacy systems, are difficult to understand and change. The programs may have been optimized for performance or space utilization at the expense of understandability, or over time, the initial program structure may have been corrupted by a series of changes. To make legacy software systems easier to maintain, you can re-engineer these systems to improve their structure and understandability. Re-engineering may involve redocumenting the system, refactoring the system architecture, translating programs to a modern programming language, and modifying and updating the structure and values of the system's data. The functionality of the software is not changed, and normally you should try to avoid making major changes to the system architecture. Benefits of re-engineering: reduced risk. There is a high risk in redeveloping business-critical software. Error may be made in the system specification, or there may be development problems. Delays in introducing the new software may mean that business is lost and extra costs are incurred. Reduced cost. The cost of re-engineering may be significantly less than the cost of developing new software. Activities of re-engineering: source code translation. Using a translation tool, the program is converted from an old programming language to a more modern version of the same language or to a different language. Reverse engineering. The program is analyzed and information extracted from it. This helps to document its organization and functionality. Again, this process is usually completely automated. Program structure improvement. The control structure of the program is analyzed and modified to make it easier to read and understand. This can be partially automated, but some manual intervention is usually required. Program modularization. Related parts of the program are grouped together, and where appropriate, redundancy is removed. In some cases, this stage may involve architectural refactoring. This is a manual process. Data reengineering. The data processed by the program is changed to reflect program changes. This may mean redefining database schemes and converting existing databases to the new structure. You should also clean up the data. This involves finding and correcting mistakes, removing duplicate records, etc. Tools are available to support the data reengineering. Program re-engineering may not necessarily require. You don't need source code translation if you still use the application's programming language. If you can do all re-engineering automatically, then recovering documentation through reverse engineering may be unnecessary. Data re-engineering is only required if the data structure in the program changed during system re-engineering. To make the re-engineered system interoperate with new software, you may have to develop adapter services. These hide the original interfaces of the software system and present new, better structured interfaces that can be used by other components. This process of legacy system wrapping is an important technique for developing large-scale reusable services. Preventative maintenance by refactoring. In this video, we are going to see about preventative maintenance by refactoring. Refactoring is the process of making improvements to a program to slow down degradation through change. It means modifying a program to improve its structure, to reduce its complexity, or to make it easier to understand. Refactoring is sometimes considered to be limited to object-oriented development, but the principles can be applied to any development approach. When you refactor a program, you should not add functionality but should concentrate on program improvement. You can therefore think of refactoring as preventative maintenance that reduces the problems of future change. Although re-engineering and refactoring are both intended to make software easier to understand and change, they are not the same thing. Re-engineering takes place after a system has been maintained for some time and maintenance costs are increasing. Refactoring is a continuous process of improvement throughout the development and evolution process. It is intended to avoid the structure and code degradation that increases the cost and difficulties of maintaining a system. Refactoring is an inherent part of agile methods such as extreme programming because these methods are based around change. Extreme programming is an iterative approach to software development. This methodology is designed to deliver the software that the customer needs when it is needed. Extreme programming implements a simple yet effective way to enable groupware style development. This improves a software project in 4 essential ways: communication, simplicity, feedback, courage. Program quality is therefore liable to degrade quickly, so agile developers frequently refactor their programs to avoid this degradation. The emphasis on regression testing in agile methods lowers the risk of introducing new errors through refactoring. Any errors that are introduced should be detectable, as previously successful tests should then fail. However, refactoring is not dependent on other agile activities and can be used with any approach to development. Example: duplicate code. The same or very similar code may be included at different places in a program. This can be removed and implemented as a single method or function that is called as required. Long methods. If a method is too long, it should be reassigned as a number of shorter methods. Software agent. In this video, we are going to see about software agent. Definition: a software agent is a piece of software that functions as an agent for a user or another program, working autonomously and continuously in a particular environment. It is inhibited by other processes and agents, but is also able to learn from its experience in functioning in an environment over a long period of time. Software agents offer various benefits to end users by automating repetitive tasks. The basic concepts related to software agents are: they are invoked for a task, they reside in wait status on host, they do not require user interaction, they run status on host upon starting conditions, they invoke other tasks including communication. Distributed Artificial Intelligence (DAI) technologies. Distributed Artificial Intelligence (DAI) is a subfield of Artificial Intelligence (AI), which is concerned with a society of problem solvers or agents interacting in order to solve a common problem, such as computers and persons, sensors, aircraft, robots, etc. A society is termed a multi-agent system, namely a network of problem solvers that work together to solve problems that are beyond their individual capabilities. Software agents have evolved from multi-agent systems (MAS), which in turn form one of three broad areas which fall under DAI, the other two being distributed problem solving (DPS) and parallel AI, that is PAI. Therefore, agents inherit potential benefits from both DAI, example, modularity, speed, reliability, and AI, example, operation at knowledge level, easier maintenance, reusability, and platform independence. Agent system. In principle, an agent-based system might be conceptualized in terms of agents, but implemented without any software structures corresponding to agents at all. A parallel with object-oriented software can be drawn, where it is entirely possible to design a system in terms of objects, but to implement it without the use of an object-oriented system environment. But this would at best be unusual and at worst counterproductive. Agent typology. In this video, we are going to see about agent typology. There are several classification schemes or taxonomies proposed in the agent research community, from which the following three are well acknowledged. Gilbert's scope of intelligent agents, Nuana's primary attributes dimension typology, Franklin and Gracier's agent taxonomy. A typology refers to the study of types of entities, and there are several dimensions to classify existing software agents. Agents may be classified according to mobility as static or mobile, presence of a symbolic reasoning model as deliberative or reactive, exhibition of ideal and primary attributes such as autonomy, cooperation, and learning, roles as information or internet, hybrid philosophies which combine two or more approaches in a single agent, secondary attributes such as versatility, benevolence, veracity, trustworthiness, temporal continuity, ability to fail gracefully, and mentalistic and emotional qualities. Types of agents: collaborative agents, interface agents, mobile agents, information or internet agents, reactive agents, hybrid agents, smart agents. Collaborative agents: they are able to act rationally and autonomously in open and time-constrained multi-agent environment. Key characteristics: autonomy, sociability, responsiveness, and proactiveness. Interface agents: they support and assist the user when interacting with one or more computer applications by learning during the collaboration process with the user and with other software agents. Key characteristics: autonomy, learning and cooperation with the user and/or other agents. Mobile agents: they are autonomous software programs capable of roaming wide area networks and cooperation while performing duties on behalf of its user. Key characteristics: mobility, autonomy, and cooperation with other agents. Information or internet agents: they are designed to manage, manipulate, or collate the vast amount of information available from many distributed sources, that is, information explosion. These agents have varying characteristics. They may be static or mobile, they may be non-cooperative or social, and they may or may not learn. Reactive agents: they act or respond to the current state of their environment based on a stimulus-response scheme. These agents are relatively simple and interact with other agents in basic ways, but they have the potential to form more robust and fault-tolerant agent-based systems. Key characteristics: autonomy and reactivity. Hybrid agents: they combine two or more agent philosophies into a single agent in order to maximize the strengths and minimize the deficiencies of the most relevant techniques. Smart agents: they are equally characterized by autonomy, cooperation, and learning. Languages for constructing agent-based systems. In this video, we are going to see about languages for constructing agent-based systems. Most agent systems are probably written in Java and C or C++. Apart from these standard languages, several prototype languages for implementing agent-based systems have been proposed that all aim at enabling a programmer to better realize agent-specific conceptions. Three paradigms for implementing agent systems have been proposed. Agent-oriented programming, market-oriented programming, interaction-oriented programming. Construction of agent-based systems language. Agent 0, PLACA, and Agent K. Agent 0 realizes the basic ideas of the agent-oriented programming paradigm as formulated by Shoham. A language that extends Agent 0 toward planning is PLACA, and a language that aims at integrating Agent 0 and KQML is Agent K. Concurrent mutate M. It allows specifying the intended behavior of an agent based on temporal logics. Agent speak L. It is a rule-based language that has a formal operation semantics and that assumes agents to consist of intentions, beliefs, recorded events, and clan rules. Agent speak L is based on an abstraction of the PRS architecture. 3APL. It incorporates features from imperative and logic programming. 3APL has a well-defined operational semantics and supports monitoring and revising of agent calls. ConGoLog. It is a concurrent logic-based language initially designed for high-level robot programming. April, that is Agent Process Interaction Language, MAIL or MAI2L, Multi-Agent Interaction and Implementation Language, and VIVA. Other examples of languages following the agent-oriented programming paradigm. Automated testing. In this video, we are going to see about automated testing. The objective of automated testing is to simplify as much of the testing effort as possible with a minimum set of scripts. If unit testing consumes a large percentage of quality assurance, that is QA team's resources, for example, then this process might be a good candidate for automation. Automated testing tools are capable of executing tests, reporting outcomes, and comparing results with earlier test runs. Tests carried out with these tools can be run repeatedly at any time of day. The method or process being used to implement automation is called a test automation framework. Several frameworks have been implemented over the years by commercial vendors and testing organizations. Automating tests with commercial off-the-shelf, that is COTS, or open-source software can be complicated, however, because they almost always require customization. In many organizations, automation is only implemented when it has been determined that the manual testing program is not meeting the expectations and it is not possible to bring in more human testers.